This video is going to be covering all the topics that you need to know for the chemistry region. Let's begin. Basics. When adding or subtracting, the answers in the equation should be rounded to the least number of decimal places in the problem. For example, if you were adding 29.35 with 45.0, the answer is 74.35, but it should be rounded to 74.4 because 45.0 only has one decimal place, so the answer should only have one decimal place. Then, when multiplying or dividing, the answer should be rounded to the least number of significant figures. So 20 times 816,000 should be rounded to 20 million because 20 million only has one significant figure. And then other rules are that zeros in between numbers are significant. Zeros after the numbers are also insignificant unless there's a decimal point, and they are significant. Moving on to conversions. In order to convert units, you need to start with your current unit multiplied by the unit you want to convert it to over the unit you already have. So if we were asked how many grams are in 5 kilograms, we start off with 5 kilograms times 1,000 grams over 1 kilogram because we're trying to get to grams, and 1 kilogram is 1,000 grams, and we'll get 5,000 grams. How many centimeters are in 3 kilometers? We start off with 3 kilometers times 100,000 centimeters over 1 kilometer equals 300,000 centimeters, and Table C shows different conversion units. Matter is anything that has mass and takes up space. So matter can be categorized as a mixture or a pure substance because if it has constant properties and composition, then it's a pure substance such as elements, but if it doesn't, then it could be a mixture. And then mixtures can either be heterogeneous, which are not uniform throughout, or homogeneous, which are uniform throughout. Pure substances can be separated chemically, such as compounds, or not, such as elements. Pure substances cannot be broken down into simpler substances. Diatomic elements on the periodic table are hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Compounds are 2 or more elements that are chemically combined. Mixtures are 2 or more substances physically combined. And properties of compounds can differ from their individual elements, but mixtures still retain the properties of their components. On to our first Regents question. Diamond and graphite are 2 forms of solid carbon. These two forms of carbon have. So diamond and graphite are clearly very different. They look different and they have different properties. Their difference in structure is what gives them these different properties. So the answer is choice 1. Which statement describes the solution of sodium chloride in water? Water is known as the universal solvent. Salts, like NaCl, are solutes, so this means the answer is either choice 1 or choice 3. Because the salt will dissolve in the water, the solution will be homogeneous or uniform throughout, choice 3. If we look on the periodic table, xenon is in group 18, so it's a gas at STP, which means that it's either going to be choices 1 or 3. Xenon is not a diatomic gas, so there wouldn't be 2 atoms together. The answer is choice 1. Physical and chemical properties. Some physical properties are properties that are observed or measured. There's no change in chemical composition. It could be a phase change, a size change, a change in the melting or the boiling point, or in electrical conductivity. A chemical change would be something that decomposes, reacts with, rusts, or is flammable. Which statement describes the chemical property of iron? So from the answer choices, the key word signaling a chemical property is reacts with. The other choices describe physical properties, so the answer is choice 3. Which substance can be broken down by a chemical change? So of the options listed, ethane is the only compound. All the other choices are elements, which can be found on the periodic table of elements, and because they are elements, they cannot be broken down much further. At STP, which property can be used to differentiate a 10-gram sample of NaCl from a 10-gram sample of NaNO3? Since the sample is at STP, the temperature is the same. Both samples are 10 grams, so mass will also be the same. In the question, it says that both samples are solid, so the phase will also be the same. This means that only the solubility in water could differentiate the samples. Separation of mixtures. Filtration is used to separate mixtures by their particle size. Distillation is used to separate mixtures by their boiling point. Chromatography is separating components through a stationary phase into different components, so it shows like the color. And then centrifuge is separating based on density. Which process can be used to separate mixtures of two liquids having different boiling points? So if you remember, I recently said that distillation is what separates mixtures based on their boiling point, so the answer is choice 2. Energy. So energy is the ability to do work. Potential energy is stored energy, and kinetic energy is the energy of motion. Heat flows from areas of high temperature to low temperature. Chemical energy is the energy in chemical reactions. Light energy is the energy of light waves. Electrical energy is the energy of electrical currents. Atomic/nuclear energy is energy made up of protons and neutrons. There are 2 types of reactions, like heat reactions. So exothermic reactions, energy is released, and it goes from chemical energy to heat energy. Examples are deposition, condensation, and freezing. Endothermic reactions absorb heat, so it goes from heat energy to chemical energy, and some examples are sublimation, boiling, and melting, and here's a chart for reference. The melting of an ice cube is an example of So the ice cube is taking in heat if it's melting, making the reaction endothermic because it's absorbing heat. It is changing phases going from a solid to a liquid, representing a physical change, not a chemical change. Here is just an image of a heating curve showing as it goes from a solid to a liquid, the object will have a melting point, and then from a liquid to a gas, it'll have a point of evaporation, and the temperature will increase. This cooling curve shows that as the substance goes from a gas to a liquid, it's going to have a point of condensation, and then as it goes from a liquid to a solid, it's going to have a freezing point. So it's the exact opposite of the heating curve. Moving on to the history of atoms, Dalton theorized that atoms are the basic unit of matter and that atoms of an element are identical. Thomson introduced the plum pudding model. Atoms are positive and negative electrons float around. He also discovered the electron. Rutherford conducted the gold foil experiment, which discovered the nucleus. He shot positive alpha particles through gold foil and they were deflected. So this concluded that the atom is mostly empty space with a small, dense, positive nucleus at the center. Bohr modeled that the nucleus was small and dense and that orbitals around the nucleus contain electrons. The current model, the wave-mechanical model, shows that electrons act like waves and particles. Electrons are found in clouds, and orbitals are inside the clouds, and orbitals are the most likely location of electrons. And here's a chart showing the mass and charge of a neutron, proton, and positron. Which phrase describes the nucleus of any atom? So from the Rutherford model, we learned that the nucleus is small, dense, and positively charged, so it will have an overall positive charge. Answer choice 1. Which 2 particles each have a mass of approximately 1 atomic mass unit? So if you look on table O, it shows the mass and charge of different particles. From table O, we can see that a proton and a neutron both have a mass of 1 atomic unit. The wave-mechanical model of the atom describes the location of electrons in orbitals outside the nucleus. This is a basic concept of the wave-mechanical model that you should just generally remember. Talking about atoms, on the periodic table, the top number is the mass number, so it's the amount of protons and neutrons. The bottom number, which for oxygen is 8, is the atomic number, which is the number of protons. The number of protons is equal to the number of electrons for elements on the periodic table. Isotopes have the same number of protons but different number of neutrons. A positive charge, such as the -2 in the corner, so for this one it's negative, but if it were positive, it would mean that there are less electrons than protons. A negative charge means that there are more electrons than protons. So oxygen's -2 charge means that there are 2 more electrons than protons. A potassium atom has a mass of 37. What is the number of neutrons in this atom? So you should look at the periodic table. The mass number is the amount of protons and neutrons, as I previously said. The atomic number of potassium is 19, so that means that there are 19 protons in the atom. The mass number 37 minus the amount of protons, 19, will give you the number of neutrons, which is 18. The atomic mass is the average mass of all naturally occurring isotopes. The formula for atomic mass is the mass of the isotope times the abundance of the isotope, and then you just add it for all the other different abundances that there might be. And you have to remember to divide your answer by 100 so that it can be a percent. Principal energy levels. The first energy level will have the least amount of energy and can hold up to 2 electrons. Then the next energy level can hold up to 8, the next one can hold 18, and the fourth one can hold 32. As the energy levels increase, there will also be more energy. If the principal energy level is occupied, then it has not reached its maximum capacity, but if it's filled, then it has reached its maximum capacity. So if in the second energy level there was 4, it's just occupied, but if there's 8, then there can't be any more. The electron configuration shows how many electrons are in each principal energy level. So 2, 5 means that there are 2 electrons in the first energy level and 5 in the second energy level. Ground state versus excited state. The ground state is stable and electrons copy the lowest energy level. All elements on the periodic table are in the ground state. The excited state is unstable, and in order to reach the excited state, electrons must go from a lower energy level to a higher energy level. When electrons go back to their ground state, they give off energy that is called atomic emission spectra. Every element has a unique color. When a ground state electron in an atom moves to an excited state, when an atom is in the ground state and moves to an excited state, it's going to go from a lower energy state to a higher energy state. By moving to a higher energy state, it must absorb energy, because then when it releases it, it's going to emit the color and go back to a lower energy state. Which Lewis electron dot diagram represents an atom of nitrogen in the ground state? An atom in the ground state is the state it's in on the periodic table, and on the periodic table, nitrogen has 5 electrons in its outer shell. Characteristics of the periodic table. The staircase on the periodic table is the bold line that goes along B, Si, As, Te, and At. Metals are left of the staircase, and they're able to conduct heat and electricity. Non-metals are to the right of the staircase, most notably group 18, which is the noble gases, and non-metals are poor conductors of heat and electricity. Metalloids are the elements along the staircase, and they have characteristics of both metals and non-metals. Some trends along the periodic table. Metallic activity increases going down the group. Electronegativity increases as you go from left to right along the row. Electronegativity decreases as you move down a group. Ionization energy also increases as you go from left to right and decreases as you go down. The atomic radius decreases from left to right and increases as you go down a group because the electron shells increase. Reactivity increases as you move down a group of metals and up a group of nonmetals. Reactivity increases as you go to the right for nonmetals and as you go to the left for metals. For metals, the ionic radius is smaller than the atomic radius, but for nonmetals, the ionic radius is greater than the atomic radius. Compared to the metals in period 2, the nonmetals in period 2 have. So, as I said previously, as you go from left to right along the row, the electronegativity value and ionization energy increases. So the answer is choice 4. The nonmetals will have a higher first ionization energy and higher electronegativity values. Which changes in both charge and radius occur when an atom loses an electron? When an atom loses an electron, it will have a smaller radius. Then, because it loses the electron, which has a negative charge, it will become more positive, making the answer choice 3. Characteristics of periodic table. Group 1 is alkaline metals. They have one valence electron and are soft and extremely reactive. Group 2 is alkaline metals, which have two valence electrons and are also soft and extremely reactive. Group 17 is halides. They are the most reactive nonmetals and are diatomics. Group 18 is noble gases. The oxidation number is 0 and they do not form compounds. They have 8 electrons in their valence shell. Bonding. Bonds are forces of attraction. The acronym BARF, as bonds are broken, energy is absorbed, and as bonds are formed, energy is released. The goal of bonding is to have a complete outer shell, which is 8 valence electrons. The law of conservation of energy, energy cannot be created or destroyed. A Lewis electron dot diagram shows the number of valence electrons in an element according to the periodic table. Which statement describes what occurs when two iodine atoms react to produce an iodine molecule? For this question, we should use the acronym BARF from the previous slide. When a bond is broken, energy is absorbed, and when it is formed, energy is released. A bond is going to be formed because two atoms will come together to form a molecule, so the answer will be choice 2. You can also use the crisscross rule when applicable. So the crisscross rule crosses over the charge of an ion to determine the ratio of its mass. It's only used for ionic compounds, so charges should be crossed over, and if necessary, it should be simplified. In the example, we have Pb 4 plus and O 2 minus. So then you cross over the charges and you'll have Pb2 O4. But this can be further simplified so that it's Pb and O2 by dividing each of the subscripts by 2. Electronegativity difference. If the electronegativity difference is greater than 1.7, the bond is ionic. If the electronegativity difference is less than 0.4, then the bond is nonpolar covalent. But if it's between 0.4 and 1.7, then the bond is polar covalent. When it's nonpolar, the molecule is symmetrical, and when it's polar, it's asymmetrical. When drawing the structural formula of compounds, you must take into account how many valence electrons each element has. Each element needs 8 electrons to complete its outer shell, except hydrogen, which only needs 2. So in H2O, oxygen has 6 valence electrons, and each atom has 1 valence electron, which means that there are 8 total electrons that we have to distribute. And then if you put a bond between each of the hydrogen atoms and oxygen, that means 4 electrons have been used up because each bond consists of 2 electrons, so you have 4 more electrons left to distribute. And then we can just put these 4 around oxygen to complete its outer shell, and hydrogen will also have its outer shell complete because it has the 2 that are in the bonds. What is the number of electrons shared between the 2 atoms in a diatomic oxygen molecule? Oxygen has 6 electrons in its valence shell, so diatomic oxygen, which is 2 oxygens, will have 12 electrons total that we can use to complete both of their outer shells. After putting one bond between the atoms, 10 electrons are left to distribute, but this won't complete both of their outer shells because if we were to distribute the 10, then each oxygen atom would only have 7 electrons in its outer shell when it needs 8. So then you can put another bond between the atoms, and 8 electrons are left to distribute, and then both atoms will have an outer shell. 2 bonds is 4 electrons, which makes the answer choice 4. Intermolecular forces are forces of attraction or repulsion between neighboring particles. The more polarized the bonds are, the stronger the intermolecular forces, which leads to higher boiling points and decreased volatility, which is the ease of evaporation. Hydrogen bonding connects water particles. This type of bonding is responsible for water's high boiling point and freezing point. Hydrogen bonds like to have FON, which means it'll happen between fluorine, oxygen, and nitrogen atoms. Dipole-dipole forces. When one pole has a partial positive charge and the other has a partial negative charge, molecules will arrange themselves so opposite poles attract. Molecule-ion attraction. Attraction within an ionic compound. Dispersion forces. Weak force between nonpolar molecules are responsible for solid, liquid, and gas phases, and they'll increase with size. Which statement explains the low boiling point of hydrogen at standard pressure? The stronger the intermolecular forces, the stronger the boiling point. So if hydrogen has a low boiling point, then it must have weak intermolecular forces, choice 4. Based on Table H, which compound has the strongest intermolecular forces at 60 kilopascals? On Table H, ethanoic acid has the highest boiling point, which means it has the strongest intermolecular forces. Vapor pressure. The higher the vapor pressure, the more molecules are in the gas phase. It's also easier to escape the liquid phase, and the substance will boil at a lower temperature. As pressure increases, the boiling point increases. As temperature increases, vapor pressure increases. As air pressure decreases, less pressure keeps the liquid in its liquid state, so the boiling point decreases. Water boils when vapor pressure equals atmospheric pressure. Gas laws. All gases are composed of particles that are in continuous random motion in all directions. They'll move in straight lines. There's a transfer of energy between colliding particles, and total energy remains constant. Total kinetic energy remains the same as long as temperature and volume don't change. The volume of individual particles is insignificant or negligible compared to the volume in which they move. No forces of attraction exist between gas particles. Hydrogen and helium act most like an ideal gas. Low pressure and high temperature is ideal. Avogadro's law is that gases at the same temperature and pressure will have. At STP, which property would be the same for 1 liter of helium and 1 liter of argon? So this follows Avogadro's law that the gases at the same temperature and pressure will have the same number of atoms. Answer choice 4. Nuclear chemistry. Nuclear chemistry studies reactions that occur because of a change in the nucleus. It makes an element a different element. There is the emission of particles to gain stability, and there is the emission of alpha particles, beta particles, gamma radiation, neutrons, electrons, and protons, all found on Table O. When one of the particles is emitted, the starting element is transformed into a different element. Matter is converted into energy, a lot of energy, because it's splitting the nucleus. The atomic number and mass must add up on both sides of the reaction. When a nucleus releases these particles, it is natural transmutation, but when it absorbs the particles, it is artificial transmutation. When one larger nucleus is split into smaller nuclei, this is called fission, and when the nuclei form a larger nucleus, this is fusion. Bombarding the nucleus is also a form of artificial transmutation. Fusion does not produce highly reactive products. That's the difference between fusion and fission. Which type of reaction releases the greatest amount of energy per kilogram of reactant? The type of reactions that release the most energy are nuclear reactions, so it's going to be the only nuclear reaction listed, fission. Answer choice 2. Given the equation representing a reaction, which type of reaction is represented? In the reaction, the two H atoms come together to form a helium atom, and in the process, neutron is released. This is an example of nuclear fusion, because two smaller nuclei come together to produce a larger nucleus. Given the nuclear equation and isotopic masses, what is the amount of mass converted to energy as a result of the reaction between the two reactant nuclei? So mass is never created or destroyed, so mass on both sides of the equation should be equal. The mass of the reactants, we should add what they give us, 6.0151 plus 2.0140 equals 8.0291. Then the mass of the products that they give us is 2 times 4.0026, which is 8.0052. If we subtract 8.0291 minus 8.0052, we'll get 0.0239 mass that is converted into energy. Half-life and decay mode. Decay mode is the type of particle that's released when the element decays. The half-life is the amount of time it takes for half of the element to decay. Both are found on Table N. The half-life and decay mode may be specified in the problem. Pressure, temperature, and the type of chemical reaction do not affect the half-life of any substance. Some important radioisotopes they might ask you about are iodine-131, which is used to treat thyroid disorders, iodine-123, which is used to detect thyroid disorders,
carbon-14, which determines the age of things that were alive, cobalt-60, which treats cancer, uranium-238, which is used for geological dating, and some risk of nuclear chemistry that they also might ask about are biological exposure, disposal, accidents, and long-term. Based on Table N, which particle is emitted by the radioactive decay of francium-220? So look at Table N and find francium-220. If you look at the corresponding row, it will show that the decay mode is an alpha particle. Which risk is related to the radioactive isotopes used to generate electricity? So of these choices, choice 4 is the only risk associated with nuclear experimentation. Which fraction of an original sample of iodine-131 remains unchanged after 24.063 days? You need to use Table N, which lists nuclides and their half-life. The half-life of iodine-131 is 8.021 days, which means that after 8.021 days, 1/2 of the sample will be left. After another 8.21 days, or 16.042 days, 1/4 of the sample will be left. Then after another 8.021 days, or 24.063 days, 1/8 of the sample will be left. The amount keeps decreasing by 1/2 of the total amount, and the answer is choice 1.